Okay, so at this point we've started looking at some basic integration tricks. We know the basic rules for, say, basic exponential functions, basic polynomials, basic trig functions, power rules. Last time we went over trigonometric integrals, like integrals with products of trig functions. And essentially the idea is always the same. Now that I have this many tricks, can I solve every integral that there is? If I can, then I'm good. If I can't, then I need to see if I can come up with a trick to solve other types of integrals. And today, we want to look at integrals that say, I have several I want to go over. The integral of dx over x squared times 9 minus x squared. And again, if we look at that, we say, yeah, anything to do with trigonometric functions is out because there's no trig functions, no exponentials. It's not a polynomial, it's actually a product of two things, but they're in the denominator. U sub is going to be out because if that's my u, that's not my du, so that's out. Well, what else could I try? Integration by parts, I could try, but it just seems like that would be really, really messy and probably not work because this is like x raised to a negative power. So how do I make that work? And this is 1 over something. And it just seems really messy. And again, the point is, okay, I have all of these tricks, none of them work. Either that cannot be integrated and we have to do something else, or I need a new trick to integrate it. And there's an idea here, and admittedly, from a student perspective, this is generally the trick that they like the least. Although speaking as an instructor, I did not like it myself all that much as a student, but speaking as an instructor, it's actually really useful. And once you see the trick, it helps you solve a lot of these. And the idea we're going to go over is what's called trigonometric substitution. And the idea is, I have a u substitution, that doesn't work here. I have an integration by parts where I create two variables, that doesn't work here. But if I kind of look at this, that's the square root of 9 minus x squared. And that kind of sort of looks like, depending on how you look at it, the distance formula, the Pythagorean theorem, things like that, which we know from trig, I can think about as just sides of a triangle, right triangle. And maybe I can somehow use that to generate a new type of substitution. And the way this works is, if you have something that looks like this, meaning, again, it kind of sort of looks like the Pythagorean theorem in one form or another, then maybe trigonometric substitution will work. What you do is, first, you draw a right triangle, and you stick a theta on there. Now, I start by trying to write the sides of the triangle in terms of this. And I will point out, your book has a bunch of formulas and tables, and if it looks like this, then do that. If it looks like that, then do this. We have established, I'm not the biggest fan of that, because more than likely, come exam time, you'll forget what all the formulas are, or how to apply them correctly, and then you just mess up because you don't remember the formulas correctly. Ultimately, if this will work, you can get it to work. And if your trick doesn't work, just manipulate things a little bit, similar to what we did with our trigonometric integrals. And here, meaning, that is a difference inside the square root, which means if I think about the Pythagorean theorem, that 9 has to be coming from the hypotenuse, A, B, C. That has to be the c squared minus a squared or c squared minus b squared, which means if that's 9, then this side is 3. 3 squared is 9. Then one of the legs has to be x. You can choose either leg. And again, your book will have ideas on, well, if it looks like this, do this one or that one. If you want to follow that, you can. Ultimately, you can try both and see which one's easier. Generally speaking, if possible, I'll let x be that side over there. And then this side of the triangle will be 3 squared 9 minus x squared, which is exactly what I have there. Now I've essentially set up a triangle that uses that information, that radical that's messing my problem up. Now I want to do a substitution. And the idea for the substitution, while it's a little bit messier, it follows the same principle as U substitution and integration by parts. I need to replace everything in that integral with stuff over here in terms of theta. So first off, let's see. Well, if I look at this, I need to somehow isolate x. So I'm going to use a trig function to use x with x and theta together because I have to relate them. And generally speaking, the way it works is two sides of your triangle will have variables in them. The third side will be a constant. Find the trig function that relates x with the constant. In this case, opposite hypotenuse. That's sine. So I get sine of theta is x over 3. Now I want to isolate x because I know ultimately for my substitution I'm going to have to take a derivative, a dx. So I want to isolate the x. So multiply the 3. I get 3 sine theta equals x. Now, again, I essentially want to check off all 3 of these things and make sure I can substitute them in. I need a dx, so I just take dx. Take the derivative here. The derivative of sine is cosine theta d theta. So now, that part's taken care of. I need an x squared. I have an x here, so get x squared. To get x squared, we'll do this in red, square both sides. 9 sine squared theta equals x squared. Now that part's taken care of. Now I need a square root of 9 minus x squared. We go back to our triangle and again, relate the thing I care about to the side with a constant. That is adjacent, that's hypotenuse, cosine. So, cosine theta equals the square root of 9 minus x squared all over 3. And then I care about the square root of 9 minus x squared, so multiply the 3. 3 cosine theta equals the square root of 9 minus x squared. Now I have this taken care of. Now I do my substitution. I rewrite my integral and substitute everything. It becomes the integral dx is 3 cosine theta d theta. X squared is 9 sine squared theta. And square root of 9 minus x squared is 3 cosine theta. Now I have everything in terms of sines and cosines. So now I simplify. Becomes the integral, the 3's cancel, the cosines cancel, and I get d theta. I'll pull the 1/9 out over sine squared theta. Now I just need to solve this integral right here. And in this case, there's probably different ways to go. In this case, sine is the reciprocal of cosecant. So this is 1/9 times the integral of cosecant squared theta d theta. Now just integrate that. And you should all know what the antiderivative of cosecant squared is. If you remember, the derivative of tangent is secant squared, so the derivative of cotangent is cosecant squared, but there's a negative there. So now I get my integral immediately, and it's 1/9, pull the negative out, of cotangent squared theta plus c. The only problem is, that's in terms of theta, my original integral was in terms of x, which just means I have to substitute back, just like my u substitution. If I do that, I get negative 1/9. Now, go back to my triangle. Cotangent, tangent is opposite over adjacent, so cotangent is adjacent over opposite. So it's the square root of 9 minus x squared over x, all of that, squared. And we have our solution. And I would point out, the integration part is, again, not all that challenging. It's the algebraic trick you do before that that we have to kind of learn. This idea of, oh, if I have a radical with multiple terms inside of it that kind of look like the Pythagorean theorem, then I set up a triangle, then I just look at my integral and find a way to replace everything in the integral with something in terms of theta. Then I do the substitution and integrate, which is generally the easier part, not always, but generally the easier part, because these will then just turn into trigonometric integrals like the ones we were just solving before. And then the last key point, just like with u sub, make sure you substitute back at the end. I will also point out, I'm going to do a few more of these because it helps to just see the trick worked out. These are this is an indefinite integral. I'm going to do some more indefinite ones. I'm not going to do the definite ones because they'll just take longer. But we understand, if this was definite, I could either switch my limits of integration like I do with u sub, or get to the end, plug in my limits, and be done. So that is not that big a deal. You all can do definite integrals. I graded your exams. It's the setup that's really the new thing to worry about. So, let's see. Next one, suppose I have the square root of dx over the square, the integral, I'm sorry, of 4x squared plus 1. And again, if we think about it, u substitution, yeah, that's a no. Integration by parts, that's a no. Trigonometric integral, no, there's no trig functions. Polynomial, no, that radical is just really making it awful. But hey, two terms in there added together, kind of like a Pythagorean theorem. So we draw a triangle. Call this theta. Now let's see. This and this are added together, which means these should be the two legs that are added together and squared to give me the hypotenuse. So I call these my two legs. Again, you can set it up however you want, but I prefer generally to go this route. So I'll call this 2x, because 2x quantity squared is 4x squared. I'll call this 1. And now this Pythagorean theorem is the square root of 2x squared, which is 4x squared, plus 1 squared, which is 1. Now I have a triangle. Now I just check off everything there. First, I need an x, and we said as far as it goes, relate the place with an x to the constant side, opposite adjacent, that's tangent. So right down here, we just say tangent of theta is 2x over 1, which is just 2x. Now I want to get the x by itself, so I divide by 2, and I get tan theta over 2 equals x. Now I start finding all of that stuff. I need a dx, so I take the derivative of both sides. The derivative of tangent, we actually just said it, is secant squared theta. The 1/2 floats along, d theta. That will give me this part. Now I need the square root of 4x squared plus 1. So I go back over here, and we said relate what I want to the constant side. This is adjacent, that's hypotenuse, which is cosine. So I can say cosine of theta is 1 over the square root of 4x squared plus 1. But I need to isolate the square root of 4x squared plus 1. So multiply that over, and I get the square root of 4x squared plus 1 equals 1 over cosine theta, which we then know the reciprocal of cosine is secant theta. And I will point out right at the outset, because we understand how my derivatives and integrals work, given that I have a tangent here, I know there's a relationship with derivatives and antiderivatives between tangent and secant. So you could have just looked at this immediately and said, oh yeah, don't use cosine, use secant. But like I was saying earlier, you can either memorize all the rules and hope you apply the rules correctly, or just look at the problem, understand what you're doing, and work it all out. Yeah, I don't think the cosine will work, but hey, if I'm trying to get this by itself, I don't want to use that, so I'll use the reciprocal. Understanding the algebra allows you to get all of these tricks to work as opposed to just memorizing them. So now I substitute in dx is equal to secant squared theta d theta all over 2. And then I have the square root of 4x squared plus 1, which is secant theta in the denominator and now pull the 1/2 out and I get the integral secant squared over secant is just secant theta d theta. Now just integrate that. And now this is a question of review. You should all know that one from Calc 1. So I'm deliberately not going to write the answer there. It's probably in your textbook somewhere. If not, it'll be in your old textbook. But again, you should know the basic integrals and antiderivatives of the basic trig functions. So I'm going to assume that you have that one memorized. And then you can just write it out, plug it in over here, and be done. But I'm going to deliberately not write it out to make sure if you don't know it, you actually take the time to find it, because we will be using these. Since we're going to be doing this trigonometric substitution, we're going to be needing antiderivatives like that for secant, for tangent, for cotangent, cosecant. So I want to make sure you look them up. So make sure you do it for that. Don't worry, we're going to do another one and I'll solve that one out completely. Probably. So next up, the fun one. The integral of dx over x squared plus 1 to the 3/2. And I'll point out, this is similar but different. Again, one way to look at it is to say, u sub ain't going to work. Integration by parts is out, not a trigonometric integral. So there's really nothing I can do. But there's two terms, they're added together. That is not a square root, but it's 3/2. So I mean, technically, it is the integral of dx over the square root of x squared plus 1 cubed. So viewed in that light, that is still a radical. So my idea about using trigonometric substitution seems viable. So we can try it again. Draw my triangle with my theta. Again, these two are a sum, which means that's going to give me the hypotenuse, so I have two legs. And I'll do the exact same setup I did before. The square root of x squared is x. I'll let that be my opposite. The square root of 1 is 1. That's my adjacent. And then the hypotenuse is the square root of x squared plus 1 squared, which is what I want. Now I set everything up again. First, I need an x, so I'll relate x and theta with opposite adjacent. So tan theta equals x over 1, which is just x, so I'm done. Now up here, I need a dx, so I take the derivative. Derivative of tangent is secant squared theta d theta. Derivative of x is dx, so that part's done. I need a square root of x squared plus 1, which is this and this. I know now that I'm going to relate these with, well, instead of using cosine, it would probably be better to go with secant, adjacent, hypotenuse. Hypotenuse adjacent. So then I get secant of theta equals the square root of x squared plus 1 over 1. And now I'm really done. I can do my substitution. Dx is secant squared theta d theta over the square root of x squared plus 1, which is secant theta raised to the 3/2. Now I just need to find a way to solve that out. But if I simplify, secant squared theta d theta over secant theta to the 3/2 is the integral of secant theta to the 1/2 d theta. And now, how do I solve that?